Hello everyone, welcome to In 5 Minutes. In this video clip we will discuss very important the frequency response function, which we have already used in couple of examples before. Define frequency response function, and to discuss few important things about it, we will first start with h of n. H of n is nothing but unit impulse response that we have already defined before. We define unit impulse response for an LTI system, linear time invariant system. In this case we have taken discrete time unit impulse response because we are talking about discrete time systems as of now. So if h of n is unit impulse response, then I can find DTFT, discrete time Fourier transform of h of n is given as h of omega, which is nothing but summation h of n into e raised to minus j omega n, where n will vary from minus infinity to plus infinity. And this h of omega is nothing but the frequency response function. So why is it called frequency response function? That is simply because it is a function of a frequency, and h of omega represents frequency response of the given system. You can find h of omega from corresponding unit impulse response by using the definition of DTFT. Or otherwise, if you remember, we had also discussed this before. If you know h of z, which is the system function or transfer function of the system, all you have to do is replace z with e raised to j omega, and that will also give you e raised to j omega, which is nothing but h of omega, which is the frequency response function. So ideally it should be written as h e raised to j omega because it represents the fact that it can be derived from h of z by putting z equal to e raised to j omega. But just to have simplicity in its notation, we use h of omega because ultimately omega is the actual variable. If you remember, the range of omega is from minus pi to plus pi. We either include minus pi or plus pi. So here I'm including minus pi with the equality sign. So there is no equality sign with pi. And unit of omega was nothing but radians. Like analog omega, digital omega is also related to digital frequency f. So omega is equal to f, and if you see, if I divide by 2 pi on both the sides, I will get minus half less than equal to, I'm dividing by 2 pi, omega by 2 pi will be f less than equal to half. So obviously there will not be equality sign on both the sides. This gives me digital frequency f. This is counterpart of analog frequency f, which is measured in hertz. But this f is unitless. That is simply because digital frequency f is defined as analog frequency f divided by corresponding sampling frequency. This is a definition of digital frequency f, and because it's a ratio of two analog frequencies, the small f becomes unitless. But right now, majority of the discussions that we're having it in the form of omega, which is also digital frequency. It is equal to 2 pi f, and omega is measured in radians. But later on there are many topics where the focus will be on small f also.